Assalamu alaikum, my dear students. Today I'm present here. My name is Shams Tanvir and I'm lecturer of chemistry department in English medium day shift of Raju Guttara Model College. So I've been assigned to demonstrate the online video class regarding the chapter environmental chemistry. So this is the chapter of second paper, and in my previous slide I've discussed some topics about this chapter, and today we'll resume from the last topic. So today we'll discuss about mathematical problems, and from Boyle's law, here I've shown you an example of a mathematical problem that a gas exerts a pressure of 99.99 kilopascal and having a volume of 125 centimeter cube at 25 degrees centigrade temperature, and now the temperature is constant here, so the Boyle's law will be applicable here, and by using Boyle's law we can easily solve this problem. So this is a mathematical problem which is pretty easier, and next one we'll see Charles law, problem of Charles law, that at 27 degrees centigrade temperature the volume of a gas is 500 centimeter cube, and if the pressure is constant, then we are seeing that the volume will be double. So if this type of conditions are present here, then you can assume that the given amount will be just double. Suppose if this volume is V, then the if it becomes double, then the second volume will be twice V, such as that. And by using the Charles law, that is V1 by T1 equals to V2 by T2, we can easily solve this problem, and you can keep this amount of temperature in Kelvin scale, or you can convert this into degree centigrade. That's up to you. Both the answers will be correct. So next one is Gay-Lussac's law. So Gay-Lussac's law, in this law, pressure and temperature will be variable and volume will be constant. So this is it's a mathematical problem of Gay-Lussac's law, and these laws are pretty much all the same. Just one factor will be constant and the other two will be different. And by using this equation, we can easily solve this problem here. So this is a problem of Gay-Lussac's law, and there are many other problems in your respective textbook. You can solve them, and you can exercise some other mathematical problems. These are just an example. You can find many more mathematical problems and many more examples in your textbook. So let's move forward, and this is combined gas law. And here we can see that, first of all, at STP, that is a standard temperature and pressure, the volume of a gas is 1000 milliliter, and we have to determine the volume of the gas at 27 degrees centigrade temperature and this amount of pressure. So this one is pretty much easier too. So we just have to determine the new volume, and at standard temperature and pressure, that is pressure will be 1 atmospheric pressure and temperature will be 273 Kelvin, and the volume is 1000 milliliters. So we have written this formula, written this information. Then by putting the values in the equation of combined gas law, we can determine the volume, that the volume will be in liter. So this is an example of combined gas law. You can find many other examples in your textbook. Then the next problem is from ideal gas equation. So in this problem, you have to watch carefully the units. The units are very much crucial here, because the value of molar gas constant, this is the main factor you have to keep in mind, because there are three units you can solve the problems. That is, one is SI unit, one is liter atmosphere, and another one is CGS unit. So in these three units, the value of molar gas constant, that is R, this is different. So I did not put the values of molar gas constant separately here. I didn't present these values, but just keep in mind that there are three values, and uh, on on the different types of units, you have to convert the values of pressure or volume or mass into those respective units. Suppose in SI unit, the pressure has unit of Pascal, in the volume has meter cube, and the other rest of others is same, and in mass amount, the volume unit of mass in SI unit is kilogram. Okay, so if you want to solve the problem in SI unit, you just have to convert all the values into those respective units. So this is a uh, key thing to remember. And if you think that liter atmosphere unit is easier, then you have to convert those values, that is pressure into liter, pressure into atmospheric unit, volume into liter, and so on, and the mass will be in gram. So the uh, when the unit varies, then the uh, units of the other parameters changes. So you have to keep in mind that the unit should be converted very carefully. Here we are solving the equation in liter atmosphere unit. So the pressure is being converted into atmospheric unit, and volume has been converted into liter. So by putting the equation, that is PV equals to W by mRT, we are solving the problem in liter atmospheric unit, and the mass amount will be in gram. If we solve the problem in SI unit, then the mass will be in kilogram. So please keep in mind that the unit will change according to the changing of the three units. So next will be Graham's diffusion law. Diffusion is a process by which a gaseous or liquid substance goes from higher concentration to lower concentration. That is, the main objective of diffusion is to uh, keep the concentration in the system in equilibrium everywhere. So diffusion means that in no section of the system, the concentration of the substance, that is liquid or gas, will be different. In every aspect, the concentration will be same. This is the main purpose of diffusion. And effusion will be like when we spray uh, anything from a pressurized can, that is body spray. If we spray the perfume, it comes out at a high pressure, it can be called as effusion. That is, the passage of gases through a small pore with high pressure is called effusion. So you can say in a way that the spraying of a pressurized can is an effusion. So there is a diffusion law of Graham, that is, at constant temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of the density. So if a density is a small d and rate of diffusion is a small r, then r is proportional to 1 by root over d. So this is the Graham's diffusion law, and next we will see a mathematical problem. And then before that, we will just take a glance of relationship between molar mass and diffusion. So we all know that density is the ratio of mass and volume, So if we put the values here, we can obtain a new equation, that is if we assume that R1 is rate of diffusion of a gas and R2 is rate of diffusion of another gas, then R1 by R2 equals to root over M2 by M1. So this is the relationship between molar mass and rate of diffusion. So technically, in a way, rate of diffusion is inversely proportional to the molar mass of that gas, square root of the molar mass. So a mathematical problem of rate of diffusion. So hydrogen gas and another gas are expelled from a porous wall, and the time taken by the two gases are 8 seconds and 32 seconds. Then we have to find the molar mass of the other gas. So by using the equation R1 by R2 equals to root over M2 by M1, we can easily obtain the molar mass of the other gas. So rate of diffusion will be like that. The rate of diffusion means the amount of unit time needed to reach to the whole amount of volume of the container. So that is the volume by time taken. This is the rate of diffusion. So the answer is here. This is the key points of rate of diffusion. Just by using the equation, we can easily determine the value. Next here is Dalton's law of partial pressure. So partial pressure will be the pressure exerted by an individual gas in a container in a non-reacting mixture of gases. It will be the partial pressure of that specific gas. So first of all, the mixture will be non-reacting, that is the gases will not react with each other in that container. Then we can assume that every gas is exerting a pressure to the wall of the container. This is called partial pressure. And regarding the partial pressure, we have Dalton's law of partial pressure, which states that at constant temperature in a non-reacting mixture of gases, the total pressure of the mixture would be the sum of the partial pressure of all the gases. So if capital P is total pressure and small p1, p2, p3 they are the individual pressure, then uh, this is the sum of the total pressure, and we can obtain a new equation. This is the equation for Dalton's law of partial pressure. So this is a mathematical problem present here. Partial pressure, that is at constant temperature, uh, every gas has individual volume and pressure. So for three separate gases, pressure and volume is given here, and the total volume is also mentioned in the question. So this is the volume of the container, and we have to find out the total pressure of the gas mixture. So by using the equation we have seen in the previous slide, we can easily uh, determine the value of the total pressure. So this is an example of mathematical problems. So this is the problem of partial pressure. Then let's come to kinetic theory of gases. This chapter is all about gas and the properties of the gas and the details of gases. So here we are seeing the kinetic theory of gases. So what does it say? It says that gases consist of small particles. It can be atoms or molecules. These are solid and elastic particles. The molecules move around in a constant velocity, and they sometimes collide with each other. So this is a no-brainer, and when the molecules move around, they stay in motion and they may collide with each other. So this is normal, and the volume of the particles is negligible with respect to the total volume of the gas or the container. So the volume of the particles is really negligible. Kinetic theory says that, and it is very negligible in respect to the total volume of the gas or the container. So this is a very negligible amount of volume. The particles exert individual pressure to the wall of the container, and it's completely elastic. It means that if they exert an individual pressure to a direction, they will bounce back and go to the opposite direction and exert a pressure to the opposite wall. So this means elastic. This pressure is completely elastic. If it exerts the pressure to the front wall, it will move, bounce back and go to the other wall and exert pressure to that wall. And it will exert pressure to every wall in 3 dimension. And finally, kinetic energy of a gas is proportional to the absolute temperature. That is kinetic energy proportional to the temperature. And there are some other theory of kinetic theory of gases, but omitting those and making things easier, from the assumptions of the kinetic theory, an equation can be obtained, such as PV equals to sorry, my bad, I have to correct this. PV equals to 1/3 mnc square. So P equals to pressure, V equals to volume, and capital N will be number of gas molecules, and M is the mass of each particle, and C is root mean square velocity. So this is a new term for us, that is capital C or a small c, that is root mean square velocity. So in the next slides we'll learn about root mean square velocity. So what is this root mean square velocity? It means that the average of the square velocities of the individual gas molecules. This is the root mean square velocity. This is the average velocity of the individual gas molecules. So from kinetic theory of gases we can modify the equation and we can obtain an individual equation for root mean square velocity. Here is the equation. We can use this equation in mathematical problems, so this will be useful. And there is a mathematical problem here for root mean square velocity, that at 27 degrees centigrade temperature and 1 atmospheric pressure, what will be the root mean square velocity of ammonia gas. So this is pretty easier, but there is also another factor we have to watch out for, that is the molar gas constant R. If we use the molar gas constant R for SI unit, then we have to convert the mass to kilogram. So please keep in mind that we have to convert the mass into kilogram. Okay, so if we solve this problem in CGS unit, then we don't have to convert the mass into kilogram, and the unit will be in centimeter per second. And if we convert the mass into kilogram, the velocity will be in meter per second. So please keep in mind. And this is the end of the slide for today, and in next class we'll discuss from ideal gas and real gases and the deviation of ideal behavior. Till then, take care of yourself. Allah Hafiz.